All right, hey AP Chemistry. So you do not have this handout and it's been shared with you in the Google Classroom, but I've kind of compiled a list of rules or steps on how you draw Lewis structures. I've adapted it from your textbook, but these are rules that I've been using since I was in college. And all of this comes from the top of my head, but it kind of summarizes what you're supposed to do when you want to draw a Lewis structure. So the very first thing is you're given the structure. It says it wants the structure for SO3 2 minus. Now, if you don't remember, this is the sulfite ion. And later on, you'll see where that -2 charge comes from. But SO3 2 minus. First step here, from the formula of the compound, count and calculate the total number of valence electrons. Write this number and keep track of it. It is your electron bank. So whenever I add up and get all the total valence electrons, I am only allowed to use from that electron bank, I call it. So remember, the valence electron count of each element is equal to the group number. And then if the compound is an ion, like the sulfite ion, you add electrons to the total for each negative charge and subtract for each positive charge. Now there's a 2 minus charge, which means later on I'm going to add 2 electrons. So right now, I'm going to get my total here. So sulfur is in group 6. It has 6 electrons, right? Group 6. Oxygen is also in group 6, and there's 3 of them. So 6 electrons times 3. And then there's the 2 electrons that I get from the 2 minus. So I'm going to add the 2 electrons from the 2 minus. If I do this, I'll have 6 plus 18 plus 2. That means I have 26 electrons total. Okay? So, this is your first step. This is how you figure out the total number of valence electrons in a compound. You add up for each element. Notice how I did 6 times 3 because there were 3 oxygens. 6 was for the sulfur, and then the 2 minus gave me 2 electrons. If this was 2 plus, then that would mean I would have to subtract 2 electrons. Okay? Alright, then the next step is attach the atoms in the compound to each with a single bond to the central atom. Now, there are 2 different ways you could figure out the central atom. One is common sense says it's the one that there's the least of, so that's common sense. Right? And now sometimes it's hard to have common sense in chemistry, I get it. But if there's only one S and 3 O's, how can you tell which O is a central atom? You can't. So S would be the central atom. If you don't want to use that rule, the other one is the least electronegative element or atom is the central atom. And we have a table of electronegativities, and we have SO3 here. Okay? S is 2.5. O is 3.5, so S is the least electronegative, it's the central atom. So I attach everything with a single bond to sulfur. S, O, O, O. Now, I'm arbitrarily coming up with this shape here. And in chapter 10, you'll figure out what the proper shape of these molecules are. You could have had 3 O's on one side, doesn't matter, as long as they're all attached to S. I'm just doing this because it looks nice and symmetrical. Alright, now, next step is subtract the number of electrons used to make bonds from the electron bank. Remember that a single bond represents 2 electrons. Now, a side note here is, if you've taken organic chemistry with me, you have done this so many times, or if you know anybody who is taking organic chemistry, we have drawn Lewis structures. So, I have 26 electrons in my bank, and I used 6 of them. Each bond contains 2 electrons. Remember that a single bond represents 2 electrons. So 2, 4, 6. So 26 electrons minus 6, 20 electrons. Okay? Now, whenever you're making these Lewis structures, the bonding electrons are all valence electrons. So we are not doing anything else. We're not going to have any more than 26 electrons in the structure, right? The core electrons do not bond. They are on the inside. They're closest to the nucleus, or they're closer to the nucleus. The valence electrons are the ones that do the bonding. So now my next step is give all atoms, so I'm going to redraw it, right? I'm going to do this again. doesn't matter, right? I have 20 electrons here. Give all atoms an octet by using the electrons remaining in the electron bank. So we have 20 electrons remaining. First, give the non-central atoms an octet by placing pairs of electrons around each atom. Those are 2 dots. That's a lone pair, we call that. Lastly, give the central atom an octet. And there are some exceptions to this octet rule. Remember, in quick check 1, I gave you the octet rule, which is all atoms tend to want to have 8 valence electrons. Some exceptions are hydrogen only needs 2 electrons, and helium. Hydrogen and helium only get like a duet. Boron does not require an octet. That just gets 6 electrons. And elements in, period 3 or higher. I thought I had fixed this typo, but good thing you don't have this handout. You can get this in the Google Docs that I share with you. Elements in period 3 or higher may have over an octet. And what I mean by that is elements that are like period 3, like silicon or phosphorus or sulfur, arsenic, selenium, thulium, all of them could have more than 8 electrons. So they could have more than 4 bonds or more than 8 valence electrons. And I could explain why later, but for now, just know that it's a rule. Okay? So I'm going to give all my non-central atoms an octet. Sulfur is clearly my central atom here. It's the one that was the least electronegative, and it's the one in the center. So I'm going to start by giving all of them an octet. Now remember, they're sharing these electrons. So right now, this oxygen, or each oxygen, has 2 electrons. So to give them an octet, I need 8 minus 2. I need 6 more. 1, 2, 3, 4, 5, 6. I'm going to subtract from here. I have 14 electrons left. Right now, why did I do that? Oxygen and sulfur technically both have these 2 electrons. They both share them. They're shared. This is a covalent bond. So I could count this as, I could double count it, right? If we both share an object, we both have it. Now, there's not 2 of the object, but we both have it. If both of us were sharing these 2 pens, I would have 2 pens and you would have 2 pens, okay? So, each oxygen right now has 2 electrons. I need to add 6 more to get 8. I'm going to do it for the other oxygen. Minus 6. I have 12 electrons. Sorry. I don't know how to do math. 8 electrons. Okay? 1, 2, 3, 4, 5, 6. Minus 6. I have 2 electrons left. It says, in the next step then, if there are any remaining electrons left over in your electron bank, and there are, they go on the central atom. So you gotta give your non-central atoms an octet, and then lastly, you could give your central atom an octet. So I'm gonna give these 2 electrons to sulfur, okay? So S-O-O-O-O. My structure is going to look like this. Boom. And now everybody actually has an octet, right? 2, 4, 6, 8. Oxygen has an octet. And if I counted it like that, every oxygen has an octet. It's got 1 bond and then the 6 electrons. And that 1 bond counts as 2 electrons. And sulfur has 3 bonds and 2 electrons. 1, 2, 3, 4, 5, 6, 7, 8. All octets. Now, where does this idea of -2 come in? That's when we do formal charge. Now look at my final step here. And I did not do my final step here because it's not needed, but it says if there are not enough electrons available to give each atom an octet, multiple bonds may be formed, double and triple. Now everybody has an octet, so I don't need to make a double or triple bond. Typically, carbon, oxygen, nitrogen may have multiple bonds. Carbon and oxygen can form double bonds. Nitrogen typically forms triple bonds. Okay? But you're going to learn something called formal charge. And formal charge can show me whether or not I could have multiple bonds. And I'm just going to explain that in this video. So I'm going to flip over and I'm going to show how we could calculate formal charge and how I can possibly have what's known as resonance structures or multiple bonds for this structure. So the formal charge tells me it's kind of a representative charge, a rep charge. And it tells me that atoms can have a momentary charge at any point because electrons are constantly moving. Electrons constantly move. If you remember from early models of the atom, electrons are always orbiting or going around the outside of the atom or outside of the nucleus. They're always moving. They're in shells. Matter is always moving, and electrons are always moving, right? That's why things typically vibrate. Things won't vibrate at 0 Kelvin, which everyone's dead, okay? So, formal charge, the way that I was taught this when I had organic chemistry, because Lewis structures all has to do with organic chemistry, is this very fancy way of expressing it as starts minus owns, okay? And starts is valence electrons, and then owns is bonds and non-bonding electrons. Okay? Now, your textbook will do this weird, fancy equation. I don't like that equation at all, right? They do something where it's like number of valence electrons and the number of electrons that it owns, and then like you do something with like 1/2 the bonds. I hate that. This is on page 404 to 405. They kind of use this starts minus owns a little bit, but hey, that was from my organic chemistry professor. But I just like to do valence electrons minus bonds and then whatever electrons it's got. Okay? So I'm going to show you how I do that with the sulfur. So for sulfur, right? This sulfur, it has 6 valence electrons. That's what it starts with. Now, with owns, it has... Oh, sorry, there's a lone pair here. With owns, it has 3 bonds. Okay? There are 3 bonds. 1, 2, 3. And it has 1, 2 non-bonding electrons. Right? So I don't know if you saw how I did that with the counting. I like that because in the textbook, it makes you do some weird mathy equation. It says something like, here, I'll move it over to your textbook. It makes you do this. It's like, use this equation. And I don't like that equation at all. So ignore that. Use mine. It's so much easier if you just do valence electrons minus bonds plus non-bonding electrons. Right, so I do 6 minus 3 plus 2. That's equal to +1. That means that this sulfur right now has a +1 charge, or a formal charge. At any point in time, sulfur will have a slightly positive charge, which makes sense because in my previous video, I noted that sulfur has its least electronegative. If you look at the electronegativity, sulfur is 2.5 and oxygen is 3.5. So if it's the less electronegative element, it's going to have the delta plus, which means the oxygens are going to have the delta minus, okay? Or the minus charge. Now notice how these oxygens all have the exact same amount of electrons and bonds. I'm going to calculate the formal charge of one oxygen, but it's going to be the same for all of them. So if I want to do the starts again, starts is 6 electrons, right? Oxygen's valence electrons are 6. How many bonds? 1. This is just for one oxygen. Let's say I'm doing oxygen A here. This one oxygen, it's supposed to be letter A, sorry, has 1 bond plus 1, 2, 3, 4, 5, 6 electrons. Okay? That's how I count that. So 2 electrons, 3 bonds, 1 bond, 6 electrons, and these electrons are non-bonding. I count them all separately. So if I want to do this formal charge, I'll do 6 minus 1 plus 6, this is 7. 6 minus 7 equals -1. And surprise, surprise, that matches the idea that oxygen needs to be slightly negative or have that delta minus. And it's going to have a -1 charge. Now, if I do the formal charge, -1 formal charge, if I do the formal charge of the other oxygens, it's going to be the exact same. So each of them have a -1 formal charge. Formal charge is not a full-on charge, right? So be careful. It's not like I'm saying It's an ion. It's not really an ion. An ion would be like sodium +1 and Cl -1, right? These are full charges, okay? That's a full-on come on. Okay, so this isn't letting me do that. All right, this is a full-on positive or negative charge, whereas these are not full-on -1 and +1 charges. They're formal charges, right? And you could read more on the definition of what a formal charge is, but it's the charge that that atom would have if all of the bonding electrons were on that atom. All right, so to do what's known as a resonance structure, right? And resonance falls on page, you could read more about resonance on page 402 to 403 of your textbook. Resonance kind of moves electrons, and typically you want to bring the minus to the plus. What I could do here is resonance typically wants to minimize the charges. Right, so do you see how I have like a +1 charge, a -1, -1, -1? And notice the sum of all of these charges. The sum of all of these charges, sum of all charges, formal charges, equals -2. And before we said that the sulfate ion is a -2 charge. That is where that charge comes from. It's the sum of all the formal charges. But resonance structure likes to try and minimize the charges. And to do that, typically we want to bring the minus to the plus. And that would be something my organic chemistry professor would be super proud that I'm saying. You want to bring the minus to the plus. And you do that with a lone pair. With a lone pair. Like this. Okay, so what I'm going to do is if I want to make a resonance structure involves making double bonds or moving double bonds, right? So I'm going to do that for this. There's only one positive or plus here, and that's on sulfur. So let's just say I'm going to arbitrarily choose the top oxygen. It doesn't matter. I'm going to move one of these lone pairs in between the oxygen and the sulfur. This is forming a resonance structure. Right? Resonance is moving a pair of electrons. And so if I do that, if I make another bond between the oxygen and the sulfur, it's going to look like this. Sulfur, double bond O. Notice how I had 6 here, now I only have 4. And then these two oxygens were left untouched. Okay? Now if I want to go and calculate the new formal charge of this sulfur, okay, oh, and there was a lone pair here, my bad. If I want to calculate the new formal charge, let's call this sulfur B, and this was sulfur A. So sulfur A, I called this sulfur A. Let's call this sulfur B. It's not different, but I want to show you how the formal charge will be different. It starts with 6 valence electrons still. Right now it has 1, 2, 3, 4 bonds. You count a double bond as 2 bonds. So 4 bonds plus 2 electrons. The formal charge of this now will be 6 minus 4 plus 2, 0. So it will have minimized that charge. And then if I do the formal charge of this oxygen up here, I'm going to call this oxygen, doesn't matter. All right, I'm going to do it of this oxygen. I'm going to call this oxygen I. So let me say it was oxygen I. I'm just labeling it so you know. All right. Oxygen I, it starts with 6 valence electrons. Right now it has 2 bonds, right? Same 2 bonds that sulfur has. And then it has 4 electrons that are non-bonding. 6 minus 2 plus 4, also 0. This has minimized the charge. And what I mean, minimize the charges. What I mean by that is before I had 1, 2, 3, 4 charges, and now I only have 2. And look at the sum of the charges. It's still -2. So this would be probably the most stabilized resonance structure because it's minimized the charge. Now I'm showing this in a video just in case questions like this come up. On the AP exam, they typically give you this, what they call the skeleton structure, but just in case there's a question about what resonance is or what formal charge does. Formal charge, you could read on page 404 to 405 what it is. It's the charge that that atom would have if all of the bonding electrons were on it. It's not a real full-on charge, okay? And you could calculate it by doing starts minus owns, valence electrons minus bonds plus non-bonding electrons. And I could make a resonance structure by moving a lone pair, okay? So I'm hoping this video was a bit of a crash course on how to draw Lewis structures. I'll have more examples and can make another example of drawing Lewis structures quickly. In the next video I'll make probably the following day, I'll probably do quick check 2 where we draw some Lewis structures and apply this whole idea of formal charge to Lewis structures. I'm hoping this video was helpful. Please leave any comments or questions you have on how to do and draw Lewis structures. And I'm hoping my steps are a little bit more simplified than the one that you have on pages 400 to 401. 400 to 401, they kind of give you steps too. You may use these steps, print out this handout. You have it in the Google Docs. I could print out the handouts for you upon request as well. Alrighty, hopefully this was helpful.